Hey guys, in this video I'm going to present a solution to problem 2 from the previous China National Olympiad, which was a geometry problem. We have given a triangle A, B, C with incenter I. Furthermore, we denote the midpoints of segments IA, AC and CI with L, M and N respectively. Let's also suppose that there is a point D inside segment AC, so that the length BD is equal to BC. Now we introduce the circumcenter J of triangle AIC and draw in the circumcircle omega of triangle JMD. Let us denote the second intersection of line JL with this circle omega by Q, and also let's call the second intersection of MN with omega P. Finally, the incircle of triangle DAB touches sides AD and BD at points E and F. We are asked to prove that lines EF, PQ and LN have a common point. I want to begin with some observations about point J, which we have defined as the circumcenter of triangle AIC. We also gave names to the midpoints of all three sides of that triangle and therefore obtain a bunch of right angles. For example, JL is the perpendicular bisector of side AI and therefore ILJ is equal to 90 degrees. Similarly, we also have that angle DMJ is equal to 90 degrees. Therefore, since points D, M, Q and J lie on a circle omega, we also have that this is equal to angle D, Q and J. In particular, we have found a second line, namely DQ, which is orthogonal to line JL. We have many more parallel lines, so let's draw them in and try to see if we can do any angle change. First of all, looking at line AI, we see that points M and N are the midpoints of AC and IC, and therefore AI is also parallel to MN. Similarly, lines AC and LN are parallel. Looking at pairs of marked lines, we see that the angle between them is IAC, which is BAC over 2, and we find the same angle at ILN, NMD, and also QDA. Now we see that since D, P, M and Q lie on omega, angles PQD and QPM are also equal to alpha over 2. Just looking at the two right angles at L and Q, as well as the two red lines passing through those angles, we see that we have an angle equality here. Therefore, the red lines LN and QP form the diagonals of a rectangle, three of whose sides we already know, namely AI, QL and QD. This is especially interesting because our intersection point is the midpoint of that rectangle. So let's extend line LN to meet QD at a point K, and we extend line QP to intersect with line AI at a point G. As mentioned, angles GLK and GQK are equal, so GLQK is cyclic with two adjacent right angles, and therefore it is a rectangle. Since GLQK is a rectangle, we can say something about our intersection point. Namely, if we define X to be the midpoint of, say, K and L, or compactly as K plus L halves, then this is the same as G plus Q divided by 2. So it is left to prove that this point X lies on line EF. So let us try to find out more about X by this definition. Looking at the diagram, I suspected that this point X might lie on line DI. Fortunately, we know how to check this because D and I lie on opposite sides of our rectangle GLQK. Namely, X lying on DI is equivalent to X being its midpoint, which is also equivalent to LI being equal to DK. However, since A, L, K and D form a parallelogram, the latter, namely DK, is the same length as AL. Since L is the midpoint of AI, this proves that indeed Li is equal to dk in length. More precisely, the vectors Li and dk are equal, from which we can conclude that x is the midpoint of d and I. It is therefore left to prove that line EF passes through the midpoint of D and I, and since we only use points A, B, C, and D to define EF, we can erase all points except for A, B, C, D, EF, and I. And now, looking at the remaining problem, which is to prove that the midpoint X of D and I lies on EF, Timo noticed that this is actually IMO Shortlist 2006 problem G4. So this is what we're going to spend the rest of the video on. To understand EF better, we first want to introduce the exterior angle bisector of angle ADB. While we're at it, let's also draw in the altitude of B onto AC and denote its intersection with AC by H. Since EF and the angle bisector of BDC are parallel, proving that X lies on EF is equivalent to proving that the midpoint of I with any other point on that line lies on EF. Since we have in-circle touch points E and F, we want to look for some opportunities to length dash. And this is why it is a good idea to choose this other point with which we will take the midpoint with I, so that we have a parallel line to AC here. Since triangle CBD is equilateral, line CI is just the reflection of the angle bisector at D about line BH, and therefore the intersection I' of this angle bisector with the orthogonal of BH through I is just the reflection of I at BH. As I said, it is enough to prove that EF passes through the midpoint of I and I', which is just the foot of I onto BH. I want to denote this point by R, and it remains to prove that R lies on line EF. We have that EF and DI' are parallel, and DE is orthogonal to BH, which is again orthogonal to II', so DE and II' are parallel as well. Therefore, EDI' together with the intersection of II' with EF form a parallelogram, and to prove that this intersection is indeed R, we only have to show that the oriented length DE is equal to I'R. Since R is the midpoint of I'R, we have that I'R equals Ri. The length of this segment does not change when we project both I and R onto line AC, because AC is parallel to Ri. Under this orthogonal projection, R maps to the foot H of B onto AC, and I is mapped to the in-circle touching point, let's say E', of the in-circle of ABC with line AC. So Ri equals HE', which is equal to CE' minus CH. We know how to express the length of the in-circle tangent CE' in terms of the triangle side lengths A, B, C. Namely, CE' is equal to A plus B minus C divided by 2. Instead of subtracting CH in the end, I want to notice that we can also subtract minus 2CH here, which is equal to CD. Notice that the triangle ABD has side lengths C, A, and, well, B' equals B minus CD. Therefore, this quantity is just the length of the in-circle tangent DE in our smaller triangle. This is the exact equality we wanted to show, and therefore we are done.